Welcome to Math 31. This is a lesson on Newton's method to approximate x-intercepts. An application, but a very different application to what we were looking at earlier. But it is a interesting sort of historical look at a method that can be used to calculate particularly irrational x-intercepts. And it is useful now when you consider calculators and how they find zeros. So the method, when we get deeper into it, will look a little familiar to you. So we looked at any graph y is equal to f at x, and we wanted to determine the value of the x-intercept right there, which is the root. Now if it's a linear graph or something like that, it's not a big deal. You set y equal to 0 and solve away, but it's not an easy thing if you have irrational roots. So what we do is we take a stab at it. We determine x1, which is an approximation of the root. Now you could be anywhere, but you do your best to pick something close. So the coordinates of that point would be x1, comma, f at x1. So on your calculator, when you're looking for zeros, you might recall that they ask you to guess within parameters of a left and a right boundary. But you do make that guess, and that's what this is too. It's your original attempt of an approximation. Then, if you were to sketch the tangent line to y equal f of x at x equal 1. What you'll end up getting is a new value. This x2 is a better approximation. It's closer to the actual root. So a better approximation of the root. Presumably better. You're probably thinking, well, how do I know that that one is going to be closer than the original one? What if the tangent line is pointing, say, the other direction? So there is that possibility. And this is why you try to make your first attempt to be as close as you possibly can. Because if you have it on the other side of a turning point, then it is going to be pointing in the wrong direction. Now you can usually get yourself out of that sort of trouble, but you are making work for yourself. So your original attempt, you want to be as close as possible, just to make it easy for yourself. Now where this is going is we go back to the idea of that tangent line and then the slope of the tangent line. And in order to get the slope of the tangent line, we do need these 2 points. And we have x1 already. The coordinates for this point would be x2. Now the y-coordinate, of course, is f at x2, but because it's on the axis itself, it's going to be 0, and that's critical. So the next step is to find the slope of the line, the tangent line, that's passing through x1, comma, f at x1, and x2, comma 0. So I'll get some space to work here. And the slope formula is y2 minus y1 over x2 minus x1. So for us, m, well, the y2 value is 0, y1 is f at x1, and then x2 minus x1, well, it would be just x2 minus x1. And then we note the slope of the tangent line is actually the derivative and the derivative specifically in this case at x1. So that is what we are trying to do. So that makes things different. So we can write this in a more compact form. So i.e. f prime at x1. So we go into this equation and we make that replacement, and it now looks like this. F prime at x1 is equal to negative f at x1 divided by x2 minus x1. And then if we clean up this proportion of this fraction, first off by multiplying and then by dividing, we can get it in this form. So x2 minus x1 is equal to negative f at x1 divided by f prime at x1. Remember, we are trying to solve for x2. So x2 is therefore equal to x1 minus f at x1 over f prime x1. Don't need that whole division symbol. So what we end up getting is a better approximation of the root. Now the thing of it is, if we go back to the graph, it may not actually be as close as a perfect approximation. So even here, when you take a look at it, it is actually a little bit off. So really, that point, when x2, your x2 value might be up the curve a little bit or down the curve a bit. So it's not a perfect approximation, but if this turns out to be x2 right there, when you plug in and get the y value, instead of being right on the axis where you want it to be, you simply do the operation again. So repeat the procedure to find x3. And the method would be the same. You just would take, to get x3, you would take the previous point, which is x2, and then you would subtract f at x2 divided by f prime at x2. You keep doing that. Same thing would be true to get a better approximation, better still approximation. x4 would be equal to x3 minus f at x3 divided by f prime at x3, and so on. Now you're thinking, well, when do we ever stop this? Answer is that you stop it when your approximations become equal. So if x5 is equal to x4, there's no point going further. Now you can always keep adding more decimals, but typically you'll be asked to get these correct to 4 decimal places. So once you've got a match on those 4 decimal places, there simply is no more reason to go on. So there is a natural endpoint. And in general, this is the method. xn plus 1. So this approximation is equal to xn, which just means it's the term before, the x value before, minus f at xn divided by f prime xn. So this is what we end up doing, or using. Need to know it well enough so that if it showed up on an assignment or an exam that you can pull it out. So it's not on a formula sheet or anything like that. And your calculator does this process. It will take your original guess within those left and right boundaries, and it will take the guess minus the value of that point divided by the derivative of that point. And then it'll do it again. And it'll do it again until it gets the type of match that is accurate enough for the decimals on your calculator. So it's quite interesting. It's an Armstrong method, meaning that it does, you're just doing the same operation over and over again, but it does work. The issue will be the calculation. So let's do a question with this, and I'll show you the calculator method for it to make things a little bit easier. So question is, find an approximation of square root 2 to 4 decimal places. And it means we're trying to evaluate x is equal to the square root of 2. Now if you square both sides, you'll get x squared is equal to 2. And then bring everything over to the left side, you get x squared minus 2 is equal to 0. So if you looked at this in a graphical sense, this would be y is equal to x squared minus 2, and you would be looking to find the x-intercepts of y is equal to x squared minus 2. So there would be the equation, there would be the graph. So we're looking for this value right there. Now, the negative one would be the same. So what we have to do is find a place to start an approximation. So the first approximation, well, let's make a reasonable one. Now, 2 is reasonable. 1 is reasonable. I'm going to go for 1. So let's x1 is equal to 1. Now 2 would work fine as well, but easy number to work with is 1. And so we go into the formula that we have, the general formula. The next approximation, xn plus 1, is equal to xn minus f at xn divided by f prime xn. So to get x2, which is what we want, we have to go x1 minus f at x1 divided by f prime at x1. And here is where we better stop and write out the equations. You see, f at x, if we use function notation, is in fact equal to x squared minus 2. And then the derivative, f prime at x is equal to 2x. Now you do have to have these expressed in function form. So they have to be in a graphical form, which is why that original question, you got to practice a little bit so that you can go approximation of root 2 and look at this in a graphical sense. But anyways, here's what we have. So to get x2, we need to take x1, which is 1, minus f at x1, so that would be 1 squared minus 2, close bracket, divided by the 2 times 1. So into the derivative. And then x2 is equal to 1 minus, well, 1 squared minus 2 is negative 1 over 2. So x2 is equal to 1 plus 1/2. So therefore, in decimal form, which is where we're going, x2 is equal to 1.5. Get some more space to work this one out, and we keep on going. x3 is equal to x2 minus f at x2 divided by f prime at x2. So x3 is equal to 1.5 minus, open their bracket up again, and we get 1.5 squared minus 2. So into the original equation, divided by 2 times 1.5. So x3 is equal to 1.5 minus, okay, now things are getting a little messy here, or they're starting to. This one isn't too bad, but 1.5 squared minus 2 is 0.25. So this can still go into your calculator pretty well. So you enter it that way, 1.5 minus 0.25 divided by 3. And you'll get x3 is equal to 1.4166, etc. Now, this is where things get a little bit messier. You would have to take, to get x4, you would have to go the previous answer, which is 1.416666, etc., minus 1.41666 squared minus 2 divided by, open bracket, 2 times 1.41666, etc. Now, it will work. And one way to use your calculator is to use your memory keys so that you can get good answers for it. So you don't have to keep keying them in. But I'll show you a real fast method that I would recommend that you do use, all based on your calculator. And I will also then bring up at the end of this, where I'm done with this example, I'll bring up the calculator and go through it. But I'm going to write out the steps first and then ask you to follow along when you can actually see the calculator. So calculator, and the way it works is you store your x1. Whatever your original trial value is, you put that number in the memory. Now, if you have a TI-83, you're going to have over 26 memories. Everything that's in sort of that turquoise color is a memory. And most of them you access by pressing alpha to get into the alpha mode. But what I'm going to do, just to save a few keystrokes, is I'm going to enter it in into my X memory. So I take the number 1, which is our original attempt, and I press store. And then I press the X key, which really is suitable for a number of variables, and I press enter. And what this does is it just stores it. So 1, store, and then X, and then enter. So everywhere your calculator sees an X from this point on, it's going to be, if it's a calculator mode thing, it's going to interpret that as 1. And then I entered this formula in. And the formula would be exactly what we have been working with by hand. X minus, and then x squared minus 2, open up that bracket, divided by, open up a bracket. Now, you actually would probably be using your regular brackets. And then I'm in the bracket below, 2x, close bracket. So x minus, open bracket, x squared minus 2, which is the original function, divided by the derivative, which is open bracket 2x, close bracket. And if you press enter, it will do the calculation with that x value of 1. And you should get it equal to 1.5. So what we get now is our second approximation, or our first real approximation, first one being just an arbitrary value place to start. So your calculator can do it quickly, but you don't want to stop there. You now take this 1.5 and you store it into your X memory again. And we're going to repeat the whole thing. So answer into X and press enter. And to repeat the whole procedure, we use the entry key. The entry key allows you to go back and redo calculations. So if you press second function, enter, once, it'll take you to the previous operation, so you press it twice. So second enter 2 times. Do not press enter along the way on its own. Second enter, if you press enter, it'll do the calculation again, and you don't want that. So you press second enter, then second enter again. You should be seeing the equation again in front of you. X minus x squared minus 2 divided by 2x. And if you press enter now, it'll recalculate, but now it's got the 1.5 in there, and that will give you x3 is equal to 1.41666, etc., like that. And we do the same thing. We enter that into your memory key. You can use whichever memory key you want, but this doesn't require the alpha key, so it's a little quicker, not much. So that goes into the memory. So store x, enter, and then we use the second enter, the entry key again. So second enter twice. Second enter, second enter, and then a real enter. And now you're going to get x4 is equal to 1.41421. So because the question was asking for 4 decimals, you keep it alive to 5 decimals to make sure you get the round right. Store this in your memory again, so into x, enter, second enter once, second enter again, and then the real enter, and you will get, you'll get x to the 5 is equal to 1.4142. And then there's a 1 at the end of it. And you'll see that we actually have this correct to 4 decimal places. So when there is a match to 4 decimals, stop. And we would now say that x is equal to 1.4142, which is a good approximation. So if you just took the square root of 2, you'd get the very similar answer. More decimals, of course, but we could work out more decimals as well. So I'm going to show you the operation on a calculator just in case there's any issues with this, and then try a few more examples. So here we are with this one, and I'm going to turn my calculator on. Hopefully. So here we have our calculator, and the operations for this previous one would be as follows. So I'm going to do the same question. I will take x equal 1, and I will store it into the x memory right up there. So just your regular x key. So 1 into x, and then press enter. So we now have it there, safe and secure. Now I enter in the formula, which was x minus f at x, so open up the bracket, and we have x squared minus 2, close that bracket, divided by, open bracket, 2x close. So now the calculation would be like that, 1.5. Common mistake is to fail to store that. I'm not going to make that mistake, at least not this time. So store into x, enter. So now we have 1.5. So the entry key, I press second enter. I press second enter again. And there's my formula now with the 1.5 in there for x. So when I press enter, then I get 1.41666, etc. Store this one into x, enter, So it's there. Second, enter once. Second, enter again. Press enter, and I get this, 4142. Now, don't stop there. I mean, we know the answer, but we have to get a match for 4 decimals. So I'll keep going, and enter that one, and then second, enter, second, enter, and then finally enter. And then now you see to 4 decimals, 4142, it does match. Now, what's going to happen on an exam with this sort of thing? I'll start you off at where I want you to start, so x1 equal this. Because really, we could have picked x1 equal 2 for the previous question. It doesn't really matter. Although, you want to make a good choice. But I will start you off, and then I will ask you to record each of your approximations. And that way I know that you're doing it, where we've all got the same answer for it. So the next example, find the smallest solution of x cubed minus 3x plus 1 is equal to 0 to 4 decimal places. Usually I'll ask for 4, but you can go for as many as is required. And if you graphed it, this is what you get. So you put it in the graphing context, and f at x is equal to x cubed minus 3x plus 1. So the derivative, f prime at x, would be equal to 3x squared minus 3. Now the smallest solution, by the way, feel free to stop me with this and then work it out on your own and check the answer. The smallest one would be this one right there. And make a good choice on what the first trial is, but I would say let x1 be equal to negative 2. Seems reasonable. And the formula, xn plus 1 is equal to xn, the previous term, minus f at xn divided by f prime at xn. So if we want to get x2, we would go x1 minus f at x1 divided by f prime at x1. So x2 is equal to x1, which is negative 2, minus, in brackets, the negative 2 cubed minus 3 times negative 2 plus 1 divided by negative 2, or 3, times negative 2 squared minus 3. Now this is starting to look like a fair bit of work. So that's why I want to do on my calculator. So I will enter store negative 2 into x. So please pause me and work this one out. But negative 2 stores into x, and then I just carefully enter x minus, open bracket, x cubed minus 3x plus 1, close that bracket, divided by, open bracket, 3x squared minus 3. So you don't need to worry about any of those negatives. So x minus, open bracket, x to the exponent of 3 minus 3x plus 1 divided by, open bracket, 3x squared minus 3. And you should get your x2 is equal to negative 1.8888, etc. So we're looking for a match. Make sure you store that into your x again. And now use your entry key twice, then enter. You should then get x3 is equal to negative 1.87945. Now when we take this one, and we recognize that it's got to get around to 4 decimals, x3 is equal to negative 1.8795. So there are our 4 decimals. Store that again in x, and then once more the entry key twice and enter, and you'll get x4 is equal to negative 1.879385. So x4, when we take it to 4 decimals, is negative 1.8794. So it's a little bit off what we had previously, so we must keep going. Store that one into your memory, go back, second entry twice, and for your x5, you'll get negative 1.879385 and some change. So x5 is equal to negative 1.8794, and that's the way we want it. So therefore, the approximation would be x is equal to negative 1.8794. Now the next example that I've got isn't really that complicated or anything new, but it goes like this. Here you're asked to get the smallest positive x-coordinate of the intersection of these two functions. And to get it going, it's in this form. You would use your intersect key on your calculator, but we want to find this. Where is the one function, x cubed, equal to 1 minus x? And we're at the same position we were earlier, because we take this equation over to one side. X cubed plus x minus 1 is equal to 0. So we want to get the x-intercept for this, x cubed plus x minus 1. And find x-intercept. In this case, the smallest positive x-intercept. So we'd be looking for this one right there. And all you need to do is the exact same method that we just did, and then check your answer. So what I'm going to do is let you do this one, and then I'm going to give an answer, and I don't think you need to see this thing again. Now the one thing with this is that it's a little bit, the graph's a little tight around the axis. And you should get, for an answer, 0.6823. And check that out, make sure that you get that. If you run into problems with it, let me know and I'll see what I can do with it. But this is how these ones work, and basically you want to make sure that you can do this method, and make sure that, given that you're starting at the same place, you get all the same approximations. Watch for the round. So make sure if it's to 4 decimals that you do consider the 5th decimal to get the round correct. So that's it for this lesson. That's it for this unit, in fact. Thank you for your time.